Today I'll be talking about an approach to natural ventilation where a lot of people are familiar with natural ventilation design. Natural ventilation design in both residential, commercial and industrial buildings is something that's been incorporated for a long time. However, with the way designs are starting to go, things aren't becoming your typical design approach. More designs are starting to vary from the norm, and as such we need to start looking into verifying how things are working, or we come up with alternative ways to make sure what we're proposing is actually working. So when we look at a wind effect on a building, there's a lot of different aspects we look at. It's not just one simple feature, and it is a holistic approach that you sort of look at. So with Windtech, we actually look at both the structural, the facade, environmental, and then goes into a lot of other aspects, including even the solar effects. For today's topics, we're just going to be focusing on one component, and even of that, an individual component of sustainable design, which is natural ventilation, and also looking at thermal comfort, which is one of the key aspects I'll go into why we consider natural ventilation. So just a bit of an outline. Essentially, I just wanted to touch on the natural ventilation design approach, how things have varied from our original approach well back in the day to how it's sort of come to now, and how essentially we started to drift away from the intuitive design approach that we've had, purely based on other parameters that have restricted what things we need to consider. I'll then look at as to why natural ventilation needs to be considered, so different criteria, so things that actually we need to benchmark against, different techniques, and then finally just touching on some case studies for non-typical structures in that sense. So essentially the sustainable design is starting to now evolve, as we heard earlier today, with lifestyle talk, life cycle discussions. We're looking more on efficiency of the design. It's more about the cost benefit. And the big key thing comes down to actually the end client. The end client wants to know what benefit will they get out of their product. It comes down to you don't put so much money up front to do the further analysis, but if they know down the track they're going to recoup it, whether it's a running operating cost or it's an end value asset that's increased. A lot of research has sort of gone into that, and as was also discussed, it's been driven mainly by the governments themselves. One of the key things actually in Australia, you look at all the capital cities, the big thing that actually is driven by an environmental approach to sustainability for their design is based in the capital. And that's because that is where the government's heavy influence in office occupancy. And if you're not sort of at that higher range level, then the occupancy rates actually are through the roof, whereas it's quite tight for sort of a high-grade sustainable building. There's also other things that are driving the aspect. There's a discussion from a social point of view. There's government regulation parameters. There's also restrictions on sites for power consumption. That's in a way, you have a regulation approach from the government, but also allowing the client to only have so much power for their site. So it's a different approach that you need to actually deal with, and that's where natural ventilation, in a way, is coming about to try and reduce the mechanical load. So with regards to that, with the design, we originally started out, the projects are actually located, when you think about their major cities were located near harbour towns. They're located near where we actually had a functional use for it. So might also be right near a coast. A lot of buildings weren't or cities weren't developed inland as much. They were developed near things where they had resources, whether it be natural resources for production of a supply of something, or for actual it's just beneficial for use. So near a water body, near the coastline, near a cooling breeze and so forth. And we sort of intuitively adapted that to our design approach. However, as things have developed and the pressures to continue the expansion of everything, we brought new cities were developed, and as such the sort of, I guess, the sort of inert design that we had all inside of us, it started to drift, where there was also concepts of you could just get one single design and start plonking it anywhere in the world. We're not looking at the actual locality of the project. One of the things you actually need to start considering is, and this is just an example from the project we've been going through with that client, is actually looking at where the site's located to start off with before we actually go down the track. So in this case here, it's actually looking at, it's looking at the site's located in this central part, and we're looking at where the ridge lines are located on the site, so how that can affect potentially the actual flow around the site, the prevailing winds, both from a summer point of view and an afternoon, and also the actual solar path itself, so where those actual angles are that can affect the site. It's instead of, and then from this approach, you can sort of, instead of viewing it as a restriction on the design, it's viewed as something that can be enhanced onto the design approach itself overall. Now, government regulation, this is one simple case that's been brought up. They try to provide some guidance as to what can be done. So in this case here, it's sort of saying a single aspect apartment, so apartment located mid-span of a building, they don't consider it to comply. From a wind engineering point of view, we know that you can generate pressure differentials to provide natural ventilation, but they try to keep this, the typical norm where you have your rectangular or square plan-shaped buildings. Their consideration is only that if you have, say, a corner apartment or a crossover apartment, or in this case, a mezzanette apartment, is considered naturally ventilated. If something varies from this, they just won't view it. And so it becomes an education thing from the regulatory body to actually help them understand this. And this all leads to, because the design for some typical buildings in suburbia comes down to very simplified approaches. So if you can see here, this is just a perfect case of you have prevailing winds coming in from this corner here. So they consider corner apartments are working, you've got a crossover apartment, other corner apartments. However, they wouldn't actually even start considering apartments on this site. They actually just start looking at the very simple approach. The problem is, however, buildings aren't typical anymore. These are different examples. This is Habitat 67. This is an example of a project we're working on at the moment. So the concept of trying to just include a recess because that'll provide a pressure differential doesn't really work. Because you can see in here, this area there, the pressures don't stagnate. So you're not going to get a differential pressure generated. So you're not going to get natural ventilation.
在这里呢会有一个，那么我们可以看到，在这里是没有压差的，因为它压力那么是固定的，所以我们应该在这里那么看一下。
Approach, we need to provide some measurement of what natural ventilation is, and simply putting a couple of colour lines on the plot, as we started to see with more education of people, essentially the powers that be, they understand that a colour line doesn't make something work, and that's for essentially any of our industries. So what parameters should we consider then for natural ventilation? More importantly, why should we even bother? So two main key parameters and this is what the whole natural ventilation is about. It's looking at air quality and it's looking from a thermal comfort point of view. So air quality is looking at contaminant-based relations. So all of us in this room at the moment, we've all got a body odour. We're giving that off. And then the furniture in this room, the finishes on the walls and the ceiling and so forth, provides an odour. So the whole point of the air quality is to provide that circulation to essentially provide fresh air. Otherwise things become stuffy, you end up getting contaminant build-ups, above certain international standards and so forth, so you end up getting what they call the sick building syndrome. The other part is to look at the actual thermal comfort. So when we design for natural ventilation, it's all well and good you have windows that are there, but the reason you're doing that sort of path is to remove the reliance on mechanical ventilation. So if you're not actually able to provide a thermal comfort for the occupants, then where are you sort of left standing? So there's a couple of different international standards that relate to air quality. These are just two examples, which is Australian standard and also American standard. So the parameters they sort of base around is what the intended use is, materials used, number of occupants and so forth. And so these sort of parameters, they give you guidance as to what the typical density is, but they typically result in around about 2 or 3 air changes per hour. And that is simply just looking at a circulation of supply. From a mechanical point of view, typically that becomes a bit higher because you're dealing, compared to a fresh air solution, you're dealing with a supply air. So it's a different, typically they look at sort of a 5 up to 10 air changes per hour as opposed to a fresh air solution, which is around about that 2 or 3. From a thermal comfort point of view, this is where it becomes a little bit more complicated per se. So the plot on the right over here discusses you got a flow velocity against a cooling sensation. So this is research done. This is sort of comes back to essentially when you hear you get the thermal cooling that people have. And there's a lot of different aspects. You could be in the cold, where you get that wind chill that occurs, or it could be in the hot, where you start perspiring, and the airflow of your body that's been perspiring provides that cooling sensation. Your body re-regulates itself. But then it comes down to also, well, what is the climate that you're in? So there's mild climates, you sort of, in the up to about 30 or so degrees. Then you start getting your warmer climates. But then what about warmer climates again? So areas where we're hitting well above 40. I mean, perfect example is in the Middle East at the moment. It's around 45 degrees week in, week out. During summer or higher again. A couple of these research papers actually looks at that concept and looks at the way people adapt, the difference in between males and females, how they adapt, how long you've been there can affect your parameters that you deal with. But typically it comes down to, for a typical suburban area, you're looking around about between 19 and up to about 28 degrees is considered a thermal range or a comfort zone, especially when you start looking at the psychometric charts. And that's where it also falls between. So the next part is then, well, what's the difference? How do you compare air quality compared to thermal comfort, and should you be considering a different aspect? And the age-old thing, if someone wants fresh air, why don't they just open the window? This is one of the reasons why you need to start considering the difference. This is for the exact same site, and it's purely looking at, on the left here is looking for a complete set of data and looking at the prevailing winds, the frequency of wind direction, and also the annual wind speed. Whereas on the right here, we've now gone into further analysis, which is what we do for these studies, and look at, well, what's the frequency of wind conditions and what's the velocities that occur during times when the temperature itself is in these range, where people actually make use of natural ventilation. So that's why we look at two different aspects. So it's all well and good. Air quality can be something, if it's cold, if it's hot or anything, if you don't like a smell that's in the room, you'll open the window, flush it out, close the window again, you're happy. Thermal comfort is something that you only utilise when you find the outside conditions suitable. On the flip side then is, well, if I just flush out the whole area, surely that'll work. But there's also becomes limitations. People perceive when you're indoors that you're in a controlled environment. So if you think about when you go to a cafe, if you sit at a cafe, you're sitting outdoors, you're happy with some sort of breeze if it does occur to come over you, because you consider yourself in an outdoor environment. If you instead move yourself into the inside of that same cafe and you feel a breeze come over you, you start questioning why. You start thinking, I'm in a controlled space, I should be able to, I should feel all these breezes and so forth, all the natural elements. You don't want, for instance, also have rain coming on you if you're inside. So these are some of the limitations that comes from a wind speed point of view. So you can't just have endless amount of airflow. And this also gets restricted based on if the occupant themselves can control the thing. So if they can go to the window, open or close it, obviously they relax their criteria. If they have access to be able to change clothes, once again, relaxes again. So there's all different parameters that do come in. So there's two key ones that we look at, and that's a draft criteria. That's actually something that's based from, that's in ASHRAE. And it looks at 1.2 or 0.8 to 1.2 metres per second for a daily average wind speed. And then based on Davenport, where we have the short duration, so we sort of look at the more critical, so more like a restaurant sort of environment because you're in indoor space. And that's what we get 3.5. So natural ventilation modelling can be done in a couple of different ways. You can look at the pressures at the openings. So depending on where the openings are, your pressures will vary. And this is one of the things that does drive the actual flow through the person's apartment or internal volume. The arrangement of the openings themselves can obviously have an impact on how the flow works. So the more internal restrictions, so doorways and so forth, can slow up the flow. The restrictions on the outside areas can also have an effect, so what's known as your discharge coefficient, to limit your flow. And that's why there's all the parameters about the distance between openings based on floor heights. It's more to be able to make sure that the closer it is to an opening, the less dissipation there is, so the better opportunity there is for it. And then it comes down to the final part, which is one of the areas that when we look at natural ventilation, where we have thermal impacts. And that's looking at a hybrid model between a wind tunnel study and a CFD model. The benefits of this is where you start looking at the wind tunnel model provides the accuracy and the pressures on the external form of the building, while the CFD model allows allowances for internal heat sources and provides better visualisation of the internal flow where that's needed. So the initial phase, and this is why I was just highlighting with regards to wind tunnel modelling, these are two examples of why it becomes quite critical. On the right here, you've got, this is a 4-tower project we're working on, in a dense environment. Now trying to pick up the effects of all these buildings for 16 different wind directions, both from a time point of view, an accuracy point of view, and a budget point of view for the client, starts to blow out. And furthermore, as with regards to when you start looking at CFD models, you need to then validate it, which becomes the harder part. The one on the left here just sort of shows one of the critical part is the gap between these two buildings is quite tight. So we're actually just making sure that, with the wind tunnel, we can actually account for that. Whereas for the CFD, you have to then start looking at the grid dependency and everything like that to make sure you're picking up the correct pressures. CFD, on the flip side, has its benefits over wind tunnel. And this is the second stage of this. So on this project here, it's a low-rise project. This is actually the Global Change Institute. So what we looked at is they've got, on this external form, they had a number of different scenarios for sunshades which rotate and track the sun, which we modelled a number of different cases in the wind tunnel. I think this was in the closed position that they had. They also had an ETFE roofing system, a thermal stack at the rear here, and a number of openings located behind. So what we can actually account for in the CFD is once we've got the pressures at the various openings located near the thermal stack and also on the external form, is look at solar heat gain. So both on the actual, because this is a large atrium at the back here, see how the sunlight came through. So you had heating of the floor surfaces. You had this thermal chimney was actually a metal element, so you could actually account for how the actual thermal flow would occur. And furthermore, as we can see on the diagram on the right here, we can actually get an understanding of how the actual circulation starts working. And it starts to help pick up, this is just one of the levels, but you can actually also see a convection flow happening in where during the summer months, cool air was coming at the lower levels and pumping out the roof at the upper levels, even though this was only a 4-storey building, whereas during the night time, the whole process reversed. So you actually had flow coming at the upper levels and coming out through the base. So there's benefits when you're actually taking the whole process, but there's also limitations on both. Obviously, with wind tunnel studies, there's limitation if you can visualise the actual flow. If you want to have an understanding of are we getting full circulation within the space or not. There's also a heating and cooling effect. So if you actually have a mechanical system or a mixed mode sort of system, or even density of people, so for instance taking the heat source associated with everyone sitting here, you can't really adapt for that in the wind tunnel. On the flip side, as mentioned, computational models have their limitations, and that's why providing a hybrid approach gets the best of both worlds and improves the accuracy. So I'll now touch on 2 case studies with that in mind. These are 2 high-rise projects that are recently being done. The first one I'll be touching on is the Greenland Centre in Sydney. One of the studies we looked at from a natural ventilation point of view from a purely wind tunnel study. We were able to get involved at the early stages and we looked at trying to optimise that process. We actually ended up doing a pilot study because one of the key elements of the Greenland Centre was making sure they provided the optimal level of comfort for the occupants on what they call these Sydney winter gardens, which I'll touch on. The Aspire Tower takes a different approach in the sense that it makes use of a large internal atrium to ventilate a number of single aspect apartments. So the Greenland Centre, which is located in Sydney, it's actually a bit of background behind it. It's actually, this lower section here is an existing building, which they're putting perimeter columns on the outside, having a large transfer level, and they're building a brand new structure on top, so retaining the original building without demolishing it. The balconies that are located on this aspect are your typical open balcony areas. From your transfer level going up, they have what they call these Sydney winter gardens. Now, Sydney winter gardens will provide a high level of comfort for people making use of an extension of the living space. This is just looking at this corner apartment on the far side. So it opens up the whole internal volume while still providing airflow through openings located at the top here and also at the bottom. So the whole thing is to essentially make the apartment bigger than what it actually is, but provide the comfort that they know that the end purchaser would desire. So the initial start we looked at, we actually made a study model of the building. We've done obviously a number of different studies, looked at including structural optimisation of the building. So we looked at the actual pressures that were located on various aspects of the tower itself. It was tested in the wind tunnel to be able to account for all the effects. As I was mentioning, we're actually looking at some key, one typical apartment which would be viewed normally as acceptable, which is a corner apartment. From the wind tunnel data, we came up with 14 different cases or critical cases to consider. The first 7 is dealing with a weekly wind speed, whereas the last 7 is dealing with a daily. What that gives us is the opportunity to understand the probability of exceedance of different wind conditions based on the data we've had. So we have made a CFD model of the actual apartment. We did a number of grid dependency studies to make sure the actual results we're obtaining, especially with regards to the flow through these openings located at the bottom and top of the Sydney Winter Gardens, to provide the accuracy of that. We're able to then utilise the wind pressures from the wind tunnel model for the flow for that. So there's a number of different boundary conditions we looked at. As I mentioned, this is highlighting the opening at the top and the bottom. And there was also these large internal openings. From this, we're able to look at how the actual circulation of the flow. So this isn't looking at, does it work? We understand from, your first principles that it will work from a ventilation point of view. What it's making sure is, because we're enclosing this large area to provide a winter garden, is there still sufficient flow? Or is this limiting the circulation? So look at a number of key aspects. This is look at the westerly winds. So you see the flow circulation coming in. This is looking at lower, so like an occupant level, so at 1 metre above ground, and this is looking up higher in the building. So you can see you've also got a convection motion inside the apartment. For the northeasterly winds that were coming through, you end up getting some unusual flow patterns within the actual space itself. But then on further investigation, we actually started picking up that it's this higher flow that's coming in through the apartment, which is further highlighted by a section view of the actual winter garden, where you get this circulation from a thermal convection model that's actually happening inside the apartment. So this is picking up the benefit of why we're doing a CFD model and this concern to actually see how there's circulation through the flow. And while these are exceeding the comfort levels I was discussing before, the benefit is with this, this is an occupant controlled environment, they can close or restrict the size of openings to limit this. The whole study was aimed at making sure we had enough ventilation. This is just for a different case. So we can see from here we've actually got exceedance of the draft criteria, which is one of the key things we want to make sure we had enough ventilation through the space, but we weren't getting too much circulation of the flow inside the area. Other studies actually and benefit from this, we looked at the wind-driven rain coming through these openings, so how that actually had rain going into the area, and also the location of even just the barbecue on the balcony space. The other project we looked at, which is Aspire Tower. Now, Aspire Tower is what will be Australia's tallest tower. If CASA has any, which is the airport regulation, has anything to do with it, this may change. So it's a 336 metre high tower. It's all residential, which we tested in the wind tunnel. We looked at a lot of the planning process we were involved very early on in the design process. One of the concepts we came up with the client and the architects is the utilisation of openings on the northeasterly, which are prevailing wind that I was discussing earlier, and the southern aspects to provide a positive pressurisation through these internal atriums. The flow could then come out through the single aspect apartments. And one of the benefits of this is you're not getting smell transfer going from the apartments back into a space where everyone's located. It's going the opposite. And this is just the view from inside the atrium itself. So from this, you're actually able to provide 100% natural ventilation for the apartments. This is not a typical design approach, and from a regulatory point of view, they considered this wouldn't work. So it shows a way that you can work around your typical solution. You don't have to always be restricted in the same sense. as I was mentioning, one of the key things that was actually brought up, which we actually work with the fire engineer and also acoustic engineer, is looking at how the flow works itself. So we had the flow coming from the atrium. It actually go through a ducting system above the bathroom area where they had sufficient space in the bulkhead. Inclusion of fire damper, limited any smoke issues that might happen from that. And then also single one-way louver system to make sure the flow itself didn't recirculate back in. So just some final comments. Natural ventilation, my other thing is you've actually got the... you can have a typical design approach, but we're starting to step away further and further from that. Having that early design input is key to be able to provide a design which is more a holistic approach. We're not looking at a project where it's a tack-on, it's an add-on feature. It becomes something that is integral part of the overall project, which it should be something that's considered for all aspects of the design. And yeah, thank you.